Hi, let's continue with section 5.5, triple integrals in cylindrical and spherical coordinates. For this section, there's no homework. To begin, let's recall something from section 2.7. Mainly, we're recalling how to go or how to convert among spherical, cylindrical, and rectangular coordinates. I'll leave this for you to reference back to. There are some times where we might have to change between cylindrical to rectangular, so it's good to have handy. Cylindrical coordinates. We already have experience with this type of problem. We're just extending it to the z-axis. And actually, we have a lot more than we experienced than we realized because we saw an example of this in the last section where we kind of work with z along with spherical coordinates. As mentioned in the preceding section, all properties of double integrals work well with triple integrals. Whether in rectangular coordinates or cylindrical coordinates, they also hold for iterated integrals. To reiterate, in cylindrical coordinates, Fubini's theorem takes the following form. Honestly, it's just as we said before. So suppose that g of x, comma y, comma z is continuous on rectangular box B, which then described in cylindrical coordinates looks like B is equal to r, comma theta, comma z of a less than or equal to r less than or equal to b, alpha less than or equal to theta less than or equal to beta, and c less than or equal to z less than or equal to d. Then g of x comma y comma z equals g of r cosine theta r sine theta comma z, which is our f of r comma theta comma z. So all it's saying is that we're able to perform this triple integral. Notice we need to add that r, just like we did in 2 sections ago when we worked with spherical coordinates or cylindrical coordinates. All right. So here we have an example of how you work with this type of integral, and it's just as you would any type of triple integral. So here we're saying that we have an r that spans from 2 to 0, a theta from pi over 2 to 0, and a z from 4 to 0. And we have our triple integral. So all we have to do is set it up. And it has it set up as r theta z. So we have to do the r d theta dz. All right, so let's set up r first. R is from 2 to 0. So from 2 to 0, then we have theta. Theta is from pi over 2 to 0, and then we have z. And z is from 4 to 0. And we're told that we're working with, let me change color, with z, r, and sine theta. And we can go ahead and first take the derivative for, and I forgot that r right here, r. We can first take the derivative for, well, we have r, the integral for r, and then for theta and then for z. But if you notice, they're all separate. We have z, sine theta, and then r squared. So if you want to, you can go ahead and separate them. Just since they're not dependent on one another. So we have r is from 2 to 0, and we have two r's. We have one r, two r's, so that's r squared. Then we can do theta separately. Theta is from pi over 2 to 0. For theta, we have sine theta. And lastly, z. Z is from 4 to 0. And whenever you can manage to split up your integrals, it makes it a lot more easy to work with. And I'll let you finish that one. Next example. Consider the region E inside the right circular cylinder with the equation r equals 2 sine theta, bounded below by the r theta plane and bounded above by the sphere of radius 4 centered at the origin. Set up a triple integral over this region with a function of r of r, comma theta, comma z in cylindrical coordinates, and include the image here. So here we can see that, well, you can split up in pieces. I think it's helpful to first start with your z. So we see that our z starts from 0 and then kind of ends at this, not point, but it ends our equation. So we can set up our z. Well, we know it. Our lowest value is 0, and it goes all the way up to this equation right here, right? That r squared plus z squared equals 16. Well, if we want to solve for z, since we're trying to find that z bound, so I have z is equal to, let's move the r to the other side, 16 minus r, and I forgot that square. Let's take the square root. So I have the square root of 16 minus r squared. It is plus or minus, but since we're working with that top part of our sphere and not that bottom part, we can go ahead and just work with that positive option. Now I'll leave that note since I know it's kind of hard to keep track of things sometimes. So it is plus or minus. We choose that plus because it's the top part of the sphere. So we set up our z. But according to our definition, we want to set up z dr d theta. Now let's talk about r and theta. So notice that it talks about that our r theta plane is bounded above by a sphere with the radius at 4 centered at the origin. So I'm going to draw that r theta plane since that's what we have left. All right. Now it says that we want the above sphere. So we're focusing on this part right here. And it has a radius of 4. All right, so from that, we can steal and create another equation. A sphere is that c squared plus r squared, got ahead of myself, not r, x squared plus y squared. We have a radius of 4, so then we set it equal to 16. Now, from here, now we're trying to see what we want. So we want that dr d theta. So it's nice to write that so you don't make that silly mistake that I was about to make. So we want r, and then we want theta. Theta is easy because we see that our angle starts from 0 and it works all its way down to 180 degrees, so that would be pi. So it goes from pi to our low bound of 0, and r, our graph goes from here to there. That is actually our circular cylinder. R is equal to sine theta. So it goes from 0 to 2 sine theta. All right, let's go ahead and put all those three integrals together. Now, it was saying just to set up. This one be kind of challenging to integrate because we have that radical. All right, so our answer would be, we want z first, since we set up for z to be first. We want dz, then we have r, and then theta. All right, so from z we set up to be the square root of 16 minus r squared to 0. R is from 2 sine theta to 0, and theta is from pi to 0. Now we're taking the integral in terms of r. Okay, let's continue with our next problem. Moving forward to spherical coordinates. Spherical coordinates are very similar to what we did before with our cylindrical coordinates. The only thing that's different is we have to kind of rewrite things so that it fits the cylindrical definition. So we can extend Fubini's theorem to spherical coordinates just as we did before and how we've been doing for this entire chapter. Don't get caught up on these values. They're just your bounds for your, so just to recall, your phi, your rho, and your theta. So they're just Greek letters, just like you have X, Y, Z. And don't let these throw you off either. That's just lowercase gamma and a psi. And we use them to just let it mean that it can be any value, and that's just a bound that we're going to label. Now notice that we're integrating in terms of rho squared sine phi sine rho squared sine phi. All right. Spherical coordinate systems work well for solids that are symmetric around a point, such as spheres and cones. Let us look for some examples before we consider triple integrals in spherical coordinates on the general region. All right. So this is just a very general example, and it just shows how we can work with triple integrals along our spherical coordinates. Don't let the notation fool you, it's just as before. So you have your rho, you have your phi, and you have your theta. So you can go ahead and try to integrate that one on your own. You should get an answer of 2 pi over 3. All right, let's do a more involved question. So this next example says set up an integral for the volume of the region bounded by the cone z equals the square root of 3 x squared plus y squared, and the hemisphere z equals the square root of 4 minus x squared minus y squared. All right. So if you would like to refer back to the very introduction of this section, I gave you that chart from 2.7 that helps us change between all of them. So it's going to be worth our time to try to rewrite this in terms of spherical coordinates. So according to Fubini's theorem that we have right above, our goal is to have d rho, d phi, d theta of rho squared sine phi. So we have rho squared sine phi of d rho, d phi, d theta. So we need to find our bounds for our rho. For our phi and our theta. Theta, we know that's just span of our angles. All right. So let's go ahead, and our job here is to try to figure out what these values are. Okay, let's go ahead and begin. So it says that our integral is bounded by the cone. So we have this cone here. And the hemisphere, so this top sphere of our value. Let's start working with that sphere because that sphere will help us find a value of our function. So let's undo that square root. So that I have z squared equals 4 minus x squared minus y squared. So when you see x squared and y squared, a red light should be going in your brain because you know you need to change that into something else, right? But we have a z squared. Do we have something that we can change x, y, and z squared with? Yeah, let's change it to the other side. So we have z squared plus x squared plus y squared equals 4. And according to our chart in the very beginning, that's rho. So rho squared is 4, therefore rho is 2. So this gives us our value for our rho. Our rho extends from 2 to 0. And that would make sense, right? Go from 0 to 2. Now we need to come up with this value b. Let's take a look at our other equation. We have z is equal to the square root of 3 times x squared plus y squared. Let's undo that square and square root and square both sides. So I have z squared is equal to 3x squared plus y squared. So let's go ahead and go from rectangular coordinates to spherical coordinates for our cone. All right. So if you recall from our chart in the beginning, that z squared is the same as rho cosine theta. And we have square root of 3 rho sine theta. So we can go ahead and divide out that theta, and we have cosine theta equals square root of 3 sine theta. And if we take the time to rewrite it, we have sine over cosine. So if we divide the cosine on both sides and get the 1/3 to the other side, we have 1 over square root of 3. Sine over cosine is tangent, so tangent theta is 1 over square root of 3. So this means that our value phi is from pi over 6, since tangent theta is 1 over square root of 3 at pi over 6. So our phi value goes from pi over 6 to 0. And then lastly, our theta goes from 2 pi to 0. Now you can go ahead and finish integrating for that integral. One more example. Convert the following integral into cylindrical coordinates. Okay, so we're going to rely a lot on that beginning chart again. So our goal is to integrate, and let's set up our integrals to what we're going to have. So we have z, r, and theta. So because of that, we're going to have an r, and then dz, dr, d theta. And this r comes from, remember, 2 sections ago, we always have r, dr, d theta. Okay, so let's go ahead and integrate, or rewrite our argument. So x is always r cosine theta. Y is r sine theta. And then, well, z is z. We're working with z, so z can stay. Z can stay. We have a variable for Z, so Z can stay. And that is our argument for our integral. Now we need to take the time to rewrite these bounds. So let's talk about each bound separately. So for Z, well, hopefully some red light should be lighting up in your head. You see those x squared plus y squared? You know that r squared equals x squared plus y squared. So if we have a square root of r, square root of r squared, that's just r. And at the bottom, we have our r squared. Let's talk more about that r and theta. So this would be like our r, and this would be like our theta, or will help us come up with those values. So for y, we're bounded with our highest value being square root of 1 minus y squared, and then zero. And then for x, we have that's between -1 and 1. All right, so for -1 and 1, this is 1 and this is -1. So those tell us that our theta is from pi over 2 to -pi over 2. And then our y's tells us that we go from, so when you have something like this, it's a semicircle. If you have a square root of a number squared minus an x squared, if it's a plus, it's the top half. If it's a minus, it would be the bottom. So because we have a positive and it's a y, it's kind of like that's this right semicircle. So that kind of gives you why this kind of goes from here to here. Not necessarily -1 or 1. I was supposed to get that from the y. All right, so this tells us that we go from let me take a step back. That's what I get for not looking at my notes. Okay. So we have our x is from, and our y is from. Our x is from 1 minus y squared to 0, and our y is from -1 to 1. So there's oh, I see what I'm doing wrong. This is our y and this is our x. So for our y's, it tells us that we have a right semicircle. And our x's tells us that we have a radius of 1. So for r, it would be a radius between 1 to 0. And that wasn't a very good explanation. All right, so for this section, there is no homework. I feel as though if you understood, if you're comfortable with it, 2 sections go in 5.3, then you're in pretty good shape. All right, this is the last section for 5.5. I'm sorry, for chapter 5. Thank you.